All right, team, let's continue on with our nomenclature. Video number 5, or 4B, I guess how you look at it. So we named the 3 different types of ionic compounds in the last one. So now we got to look at covalent compounds. And then we're going to branch acids off, which are sort of like covalent compounds, unless you put them in solution, then they form ions. So it gets a little weird. So acids kind of get their own branch of naming. Covalent compounds, I think, are fairly straightforward. So we did type 1 ionic compounds was 1, type 2 ionic compounds was 2, and ionic compounds with polyatomic ions was 3. So number 4, covalent compounds are molecules. We're going to look at binary ones only. So 2 elements, and they're covalent because they're all nonmetals. There's no metals in here. If there's a metal at this level, that's going to be an ionic compound. We'll do a whole bunch of examples on the next board. So here's your set of rules. We're going to name them exactly like type 1 ionic compounds with some fine tuning. We got to separate them a little bit, right? Even though there are no metals, no cations or anions, we're going to treat the first element. So if I have like CO2, I'm going to treat the carbon and name it like it was a cation, a metal cation, and I'm going to take the second element, in this case, if I had CO2, the second element, oxygen, and name it like it was a monatomic anion. So just like type 1 ionic compounds, even though they're not ionic, see what I'm saying? We're going to add a designation that's unique to covalent compounds. We're going to use prefixes to designate the number of each element. So if I've got CO2, I've got those 2 oxygens, I'm going to use a prefix di for that. If I've got 5 sulfurs, I'm going to add a prefix penta. So I'll list up all the prefixes on the next board for you, but I think you know them all already. There's a couple exceptions, right? If you only have 1 for the first element, like in CO2, I only have 1 carbon. I'm not going to go monocarbon. I'm just going to say carbon. The mono is implied. So if you don't see a prefix on the first element, that is an implication that is supposed to be mono, right? There's 1 there. And not the end of the world, but there's some vowel combinations that look a little weird. I'll do a few so you can see how silly they are. But if you see 2 O's together, it looks a little weird. It sounds weird. If you see an O and an A next to each other, some teachers leave it, some people don't. So it's not the end of the world. Definitely avoid the 2 O's. But I'll show you where they pop up, and you can get a gut feeling for, yeah, that sounds a little silly. So let me put the prefixes up, and then we will do a bunch of examples. Here's your prefixes for you. So if you need to put these on a note card and try to memorize these, that's great. But I think they're pretty obvious. 1 being mono. 2, sometimes you see bi or di. This one's going to be di in this example. 3 will be tri. And then starting from 4 on, that's your typical, polygons that you learn in geometry. So 4-sided, tetra, 5, like the pentagon is 5 sides. Hexa for hexagon, 6-sided. Heptagons, octagon, that your stop signs have 8 sides, the octagon. Or if you're in a UFC, all right. Nona and deca, of course, like a decade. How many years are in a decade? Boom, 10. Hey, there you go. So let's use these, and you just got to watch out for the, OO and AO combinations. So let's do a couple examples so you can see it. All right, if you're feeling gutsy, pause it, name these 3, and then take the name and go to an actual chemical formula for me. You got to be able to go both directions when you're doing it, from name to formula, formula to name. All right, here we go. I think naming these are pretty straightforward. We've got 1, we know they're binary, right? They only got 2 elements. They're all nonmetals, so we identify them as covalent compounds. They're not ionic. So we're going to use prefixes. Remember, there's only 1, so we don't go monosulfur. We just leave it as sulfur. So we're going to go sulfur, and then we got 3 oxygens, sulfur trioxide, right? If it was an ionic compound and treated it that way, sulfur oxide, but we got to use the tri to separate it from a type 1 ionic compound. So I'm going to go sulfur trioxide. Easy stuff, right? And again, don't include mono for the first element. Same thing here. So you would think it is carbon oxide, but it's not. We have to include the mono, not for the first one, but we do for the second one. So we got to use the mono for that. But watch how we got a problem here. So if we go carbon, we're fine there. But let's put mono and then put oxide. That says carbon monoxide. It's not a cow. It's not carbon monoxide. You know it's carbon monoxide. Like back in my day when we had carburetors in cars, you had to be careful working on your car in the garage with the garage door closed because you can get carbon monoxide built up and sticks to your hemoglobin and all that stuff. So you got to watch out for it. So we got to get rid of that double O and go monoxide, not monoxide. So you can see why you don't want the two O's or an O and an A next to each other. So that was pretty easy. Let's take this one. Now here we've got 4 phosphorus, so that's tetraphosphorus. We got 10, which is deca sulfide. So tetra phosphorus deca, that's 10, right? Oops, why did I put an X there? Deca sulfide. And if it was oxide, you wouldn't go deca oxide, you just go decoxide. Some people are okay with you saying deca oxide, but it looks kind of weird. I just go decoxide. Pretty straightforward, decasulfide, tetraphosphorus decasulfide. How do you know from a name that it's a covalent compound? You see the prefixes. None of the other ones have that. It's unique to them. Just like if you have Roman numerals, that's unique to a type 2 ionic compound. Oh, you're starting to recognize things now. So let's take this and go from a name to a formula. We got sulfur, so let's put the sulfur here. We've got fluorine. Now we got our 2 elements. It's binary. Now how many do we have? There's nothing there, so it must be mono. So the 1's implicit. Hexa is 6. Oh, aren't that easy? What's one of the easiest it is? Going from the name of a covalent compound to a formula. Piece of cake! Because it already tells you, as long as you know the prefixes, how to do it. I think we're good on those. Let's get to acids. Put your seatbelts on. We are going to run into 3 different kinds of acids, like we did before. Pure acids that are binary. Binary acids that are AQ, dissolved in water, your typical acid solution. And then non-binary acids, which are oxy or oxoacids, which has the hydrogen bound to an oxygen in a polyatomic ion. So let's start with the pure acids, which you don't run into in lab. You better not run into lab, hardly ever. So it looks like an acid. How do you know it's an acid? The hydrogen's the first element. That's how a general chemist is going to do it, not necessarily an organic chemist, right? They look at things a little bit differently, more structurally. So we like to place acidic hydrogens out front. So how do you know? Binary, right? We've got 2 elements there, and hydrogen's the first one. So I'm going to put binary here. So that we specify that as 2 elements. We are going to name them literally exactly like we do type 1 ionic compounds. Right? Even though it's a molecular compound, it's covalent, we're going to treat the hydrogen like an H plus cation, and then the non-metal here, the selenium and the fluoride, as if they were anions, even though they're not. Right? We can fudge it a little bit there. So this should be pretty straightforward to do. So we're going to treat that as hydrogen. Right? The cation, you don't change the name. And then you take the anion and add the suffix -ide, so that'd be from selenium or selenide. So the pure acid would be hydrogen selenide. All the other acids we're going to do will have acid in the name itself. But we're going to treat these like type 1 ionic compounds. And you know they're pure because they have a non-AQ state specified. If you do not see a state specified, assume it's AQ, because almost all the acids you're going to deal with are solutions, which are dissolved in water. So if there is no state, it's going to be assumed AQ, all right? So here, because we see that's a pure acid, it's binary, it starts with hydrogen. So we name that first one like a cation. Fluorine, root is fluor, add the suffix -ide. Don't say fluoride. I still see a lot of people doing flour there. It's not fluoride, it's fluoride. Not too bad. And this will be pretty obvious because I will put the state there. I have to, because otherwise you'd assume it was AQ. So that's your red flag. Oh, it's got the state there, starts with hydrogen, that's a pure acid. Name it like a type 1 ionic compound. Easy peasy! What if we dissolve it in water? Oh! All right, binary acid solutions. Looks a lot like a pure acid, right? You got hydrogen as the first element and some other nonmetal as the second element. But it'll either have AQ after it or no state after it. Remember, no state, we're going to assume is aqueous. So 4 parts to it. Ready? So we're going to use the prefix hydro. This is the only category of compounds that has the prefix hydro. So if you see hydro, something starts with hydro, boom, you know it's a binary acid solution. All right. Then we're going to take the root, because they all start with hydrogen, so the only difference in the name would be the non-hydrogen element, right? So in this case, it'd be the chlorine here, the sulfur there, the iodine there, because they all start with hydrogen. So we're going to take the root of that non-hydrogen element as the second part. So hydro, root of the non-hydrogen element. With some exceptions, sulfur and phosphorus are a little bit twisted from what you'd think. Then we're going to add the suffix ic, right? And then we're just going to slap acid on the very, very end. So you'll see hydro, insert root of the non-hydrogen element, ic acid. So hydrochloric acid. You'd think it'd be hydrosulfic acid, but it's hydrosulfuric acid. They keep the whole sulfur in there. This would be hydroiodic acid. Right? So let me erase the board. We'll do a few of them. You'll get a feel for it. Not too bad. Here we go. See if you can pause it and do these 3 puppies for me. Now remember, you see they're binary, 2 elements. First one's hydrogen. We know it's an acid. I see the AQ. I see the AQ. There is no state there, so I'm going to assume it's AQ. So these are binary acid solutions. Hydroblankic acid. That's all you do. And I'm sure you guys have all heard of hydrochloric acid. I think that's I think the common name back in the day was muriatic acid. You'll see that like at Home Depot and stuff. Don't quote me on that, but I think it is. So here we go. So this would be hydro. Add the root of chlorine. Chlor, add the suffix ic, and slap, because that'd be weird, hydrochloric, you need acid on the end. So that would be hydrochloric acid. So this is tellurium, is that right? Tellurium. So this would be hydro. There's the root of tellurium, telluric acid, which would just be like a sulfur or selenium, like hydroselenic acid or hydrosulfuric acid. And there's the fluorine. I got the 2 elements, starts with hydrogen. It's a solution. So hydro, the root of fluorine is fluor, hydrofluoric acid. So if you're into the show Breaking Bad, that's the acid they put in barrels and put the bodies in barrels. Oh, so nasty. All right, let's look at the last set of acids, oxoacids, and we're done with naming, guys. All right, oxo or oxy acids, I've seen both. I don't have a preference. Again, these are not binary because the acidic hydrogen is bound to an oxygen atom from a polyatomic ion. That's why they're called oxo or oxy acids. The hydrogen's bound to the oxygen atom. And that makes it acidic. But as general chemists, we like to write the hydrogen out front so we can identify the acid. But really, we should put NO3H, right? So an organic chemist would connect the hydrogen to one of the oxygens. Same with H3PO4. Those hydrogens are not bound to the phosphorus. There's 4 oxygen atoms. 3 of them will have hydrogens on them and 1 will not. Same with this one, HBrO2. That hydrogen's not connected to the bromine. It's connected to one of those 2 oxygens. So next semester, in second semester of general chemistry, we'll look at the Lewis structures of those, the expanded structural formulas, and be able to determine what makes them more or less acidic based on their structure. And you'll see those hydrogens bound to the oxygens. So that's how you recognize them. Definitely not binary, right? We've got 3 elements there, 3 there, 3 there. Naming these, let's do this on a separate board. This is, of all the categories, probably the most challenging I've seen for students. So let me lay it out for you in a tabular format. Here's a simple little chart for you. Hopefully it'll help. Do whatever you got to do to know this. So when we look, there's only really 4 ways to name polyatomic ions, right? Remember, the ones we look at have the ite and the ate suffixes, right? Usually like NO2, nitrite, NO3, nitrate, ite and ate. Ate means more oxygens. And for the halogen series, you can have like ClO minus, ClO2 minus, ClO3 minus, and ClO4 minus. So you get that whole series, the hypo, chlorite, chlorate, and perchlorate. So we really get 4 combinations. What we do is we do not alter any prefix. Like if it has a per or a hypo, we don't change that and we bring it over into the name of the acid. Then we take the root of the non-oxygen element of the polyatomic ion. So like for nitrate, NO3 minus, it's nitrogen. For bromate, it's the bromine. See how I'm saying? And then it'll either end in ite or ate. We're going to convert those suffixes into something else when it's in the acid form. So anytime you see the ite suffix in a polyatomic ion inside of an acid, it changes to ous in the acid. So ite goes to us. And if you have an ate suffix, that converts to ic. Right? So, and then you'll just add acid on the end. So if I'm going to convert this, so if I have, say, a hypobromite ion or hypochlorite ion, if it's in the acid, it will go to hypo blank, ite goes to us, and then acid. So if I had hypochlorite, it would become hypochlorous acid. If I had hypofluorite, it'd be hypofluorous acid. You see the trend? So let's look at this one. If I just had a polyatomic ion like bromite, chlorite, nitrite, something like that, you just take that name from the polyatomic ion and convert the ite to ous. So this becomes blank us acid, bromous acid, nitrous acid, sulfurous acid, right? Here, if ate becomes ic. So ite goes to ous, ate goes to ic. It goes to, if I make some kind of weird song out of that. So here you take the root of the polyatomic ion. So if it was nitrate, for example, it would become nitric acid. Right? Sulfate would become sulfuric acid. Phosphate, phosphoric acid, all those fun things. And then if you've got that prefix per, you leave it in there, and then take the root of the polyatomic ion there, and ate becomes ic. So this becomes per blank, whatever the root of the polyatomic ion is. Ate becomes ic, and you slap acid on the end. Simple little thing, right? Ite goes to us, ate goes to ic. Ite goes to us, ate goes to ic. Piece of cake. Let's do some examples. There we go. We'll switch it up. We'll do two formulas, two chemical formulas to names, and one name to a chemical formula. Got to go both ways, right? So we know it's an acid because it starts with hydrogen. We know it's not binary because there's 3 elements, right? So we can't do pure acids or binary acid solutions. So these are oxy or oxoacids. So you have to identify the polyatomic ion in order to name it. If you don't know the polyatomic ion, you're toast. So this is IO3 minus. I know it's a -1 because it's only bound to 1 hydrogen, which is a +1 in that scenario, right? Sort of. So this is, let's see, so IO is hypoiodite. IO2 is iodite, IO3 is iodate, and IO4 is periodate. Oh, know your series, just like the chlorines. So this is the iodate ion. Note the 8, that's going to become ic. So when we convert this, we take the, and there's no prefix, we don't have to worry about it. So this becomes iodic acid. Right. Iodate, if you make an acid out of the iodate ion, it becomes iodic, 8 to ic, iodic acid. Let's look at this one. So I've got 2 hydrogens, so this must be the dichromate ion. If you don't know that, you're toast. So that is Cr2O7 2 minus. I know it's a 2 minus because it's with 2 hydrogens. So that is the dichromate. 8 becomes ic. It's the exact same scenario, but that's part of the name. So it becomes dichromic acid. Let's write that in there. Now there are no states written here. You're not going to see these in their pure state. They're always going to be AQ. So any acid without a state shown is automatically going to be AQ for you guys. Remember that. Now here we got to go from a name to a formula. So we need to figure out what the polyatomic ion is and what its charge is, and that'll tell us how many hydrogens we need, just like putting together an ionic compound. So let's see what we got here. You ready? Perchloric comes, remember ic came from 8, so this comes from the perchlorate ion, right? So the ic came from 8, bring the per. So if you don't remember what that is, perchlorate is the one with the most number of oxygens. So that's ClO4 minus. That's the perchlorate ion. So we're making an acid out of that. Since that's a -1 charge, we need 1 hydrogen to cancel it out. So that becomes HClO4, one of the strong acids, one of the 6 strong acids, right? The key is knowing your polyatomic ions. If you have trouble with them, you're going to have a really hard time naming these oxoacids. Woo! There you go, my friends. That's nomenclature for you. You can do this.